I'd like to remind you the 3 stages. First stage is to describe the observations. When we make an experiment, we have to first describe the observations. Second, we have to try to infer the characteristics of the population. So we need to generalize the results. And third, we have to take decisions. So when we talk about describing the observations, we can do this by calculating some statistics about the sample. But more often, we fit a model into the data. And yesterday, we fit this model here. Perhaps you start familiarizing with it. We said that the observations, y, are expressed as functions of 3 components. The first one is a common component, that is the overall mean, which we call mu. And that's the same. It's a sort of baseline level for all the observations. Okay? Then we have a second component, which is very interesting, because it's the effect of treatments. That is something which is added or subtracted from the overall mean. So there will be some treatments which will give a higher value with respect to the overall mean, and other treatments which will give a lower value with respect to the overall mean. And that's the effect of treatments. Every observation has its own effect, but observations belonging to the same group, to the same treatment, will share a common alpha value, right? Then we have the third component, which is purely stochastic. So every observation has an error which is specific to that observation, and it relates to sampling error or measurement error or whatever. But it is important that this error is completely stochastic, completely random. There should not be any component which is shared by all observations. So all observations must be different in respect to the stochastic components. So you see that the first component is mu is common to all observations. The second component is common to the observation belonging to the same treatment. And the third component is different for all observations. So this is the important part, which we are going to talk about today. Let's concentrate on the residual. Look at this equation here. I'll make it bigger. All right, so we assume that the random component follows a certain statistical distribution of probability. So there are, this is, we are no longer talking about cause-effect relationship. There is an intrinsic cause-effect relationship, which is mu plus alpha, but then the outcome is totally random. So that means that when I make an experiment, I can obtain a lot of different outcomes. Some outcomes are more likely, some other outcomes are less likely, but I can get an infinite range of outcomes. That's the situation when I make an experiment. And these outcomes are randomly distributed according to a Gaussian distribution with a mean equal to 0, which is the characteristic of random error. You remember perhaps from the first lesson, random error is totally random, so we have the hope that in the long run, all errors sum up to 0. That's our approach. And that is expressed by this equation here, which is not really an equation because we are not writing epsilon equal to something. We say epsilon is distributed as something. That is important. It is Gaussian and mean 0 and the standard deviation is equal to sigma. So one value of standard deviation which is common to all observations. Meaning, in the experiment of yesterday, I had 16 data. So I had 16 residuals. If I pick up a subsample of these residuals and I measure the standard deviation should always be the same. Not really the same, but very similar. Because if I pick up 4 observations and they have a very wide standard deviation, then such an assumption is not valid. If we build our model like this, we need to make sure that the model fits to the data. And I have no problems about mu and alpha because they certainly fit the data. Because I'm using the means, the group means to build the model. But I am not sure about the stochastic component. I am not sure that the stochastic component is really Gaussian, and I'm not sure that the stochastic component is homoscedastic, meaning same standard deviation for all observations. Right, so these are some basic assumptions which I need to make sure of. So yesterday we fit the model. We did not get concerned with such assumptions, but today we need to be concerned about the assumptions. So I'm closing this presentation here and switching to the next one, which I still have to upload to Unistudium, but I will do it today. So here we go. I'll make it slightly bigger and single page. Yeah. So that's checking the basic assumptions for linear models. It's like, you know, making the hematological analysis. When you go to the doctor and he says, so, okay, let's check your blood and see whether everything is good. It's like here. We make some analysis to test whether there are some hidden pathologies within the data. And we need to take a decision with that respect. So we need to decide whether the data is okay or there are some intrinsic pathologies. And we are not only checking the data, but we are checking the residuals. That's our main job. And if we want to check the residuals, we need to have the residuals. So first, we need to fit the model. Second, we need to calculate the residuals. And third, we need to check the residuals. So it's a sort of post-hoc check. We cannot check the data before fitting the model. We need to check the data after fitting the model. So it may not seem obvious, but it's the way we have to do. So let's start R. I think it's better if I increase it. So let's do 18. That should be better. Is it better? I open a new script file. So we will start a new analysis now. And first of all, we clean the workspace as we did. And that's necessary for me because my workspace is always full of lots of things. Second, I'd like to load the same file as yesterday. So I need to find a way to fit everything on the screen. So I'll do like this. Sorry. Oh gosh, today it's not my day. Okay. Now, I need to fit this on the screen, so I'll do like this. I'll define a variable file name and assign the name of the file, including the path. So it's HTTP, maybe we need an S here, it's not compulsory, HTTPS www.casaonofre.it/ here datasets mixture.csv. So that's the name of the file we used yesterday. Then I can load the file by using the read_csv function, passing through the file name. So 1, 2, 3, and we see the data set here. Now, what we do is just to fit the model at the beginning, because we cannot check the data before fitting the model. So we fit the model, we check we fit the model by using the lm function as we did yesterday. And the response variable is the weight. Look at the capital letter for W at the beginning. Then we need to press the tilde. Today I'm having less problems because I have the Mac, and with the Mac, the tilde is on the keyboard. We have to do Alt and 5. But I put it on the chatbot so that you can copy it from there. And then the explainer, you remember we dropped mu because it's not necessary, because it's common for all observations. So we need to write treat. That is our explanatory variable. And we drop the epsilon because that's included by default IR. So we don't need that. And we need to specify where the data, the vectors are located. Yesterday we made 2 exercises where this was not needed because we had 3 vectors in the workspace, but not now. Now we have a data frame with vectors inside, and R cannot see the vectors inside data frame. So we need to specify where the vectors are. So we fit the model, and yesterday we the variance partitioning. we need to check the model. And we need to check the residuals. What the epsilon are obtained as by using the function residuals. Residuals from mode. That's quick. Here are our residuals. And the question is, are the and homogeneous? So this is our question, which we want to answer now. Right? And how do we answer this question? We have two possible lines of attack at this stage. The first line of attack is to make some graphical analysis. It's like taking a look, visualizing. So nothing to do with statistics. We just visualize. In my opinion, visualization is the best gun we can have to spot possible deviances. But it doesn't give us the possibility of deciding yes or no. So you can spot problems, but you cannot answer yes or no. Is there a problem? Yes or no. We see that there are some problems, and if we have some experience, we can take decisions, but we do not have a real support. To me, I do not need statistical support to take decisions about the residuals. So I strongly suggest the use of graphical methods, visualization methods, and we will talk about that. There are also some statistical tests we can use to take decisions on a statistical basis. I do not recommend them, but some reviewers do. So we need to be able to use them. So one plot, so graphical methods. One type of plot we can do is this one. I need to open the graphical window here, otherwise you don't see anything, and neither do I. We can plot the epsilon against, so you see epsilon as a function of, same syntax here. It's a formula. I plot the residuals against the fitted values. So fitted mod, because our model object is called mod. So I'm plotting simply the residuals against the fitted values. This is important. I'll show you here. Okay. Maybe we can add an horizontal line, h horizontal at y equals 0. So maybe we can even make it dashed. Here we go. So what do we see here? This is the mean of residuals. And we have the groups here. So this is the first group, the group with the smallest weight. That was the mixture, if you remember well. Then this is the group with the second, the smallest weight. That was metribuzin. This was rimsulfuron, and this was the untreated control. And we see the width, the distances of residuals from the group mean. And this makes us see whether the variances are homogeneous. What we see here is that this variance is slightly higher than the other ones. But that's not enough to make up feel that there is a problem. It's like, having sugar content in blood that's 98. So you know that the limit is 100. If you have 98, okay, you're close to the limit, but you're still okay. And this is like here. But of course, to pass you some experience, I will show you some types of graphs you can find. So remember, the first graph which we look at is the plot of residuals against fitted values, like we did here. And I want to tell you that there is a simpler way to do this, which is the way I recommend. And it is this one. You use the function plot and pass the model object with a specification which equal 1. If I do so, I get exactly the same graph I was talking about before. And you see, that's it. It's the same one. And it's more informative. You see, residuals against fitted. Here I have the fitted values, and here I have the residuals. Yeah, I want to show you some possibilities. Here we go. This is a graph. This is a good graph. All points are randomly put in that graph. So we see no patterns of any kind. The dots are just there by chance. No systematic pattern. And that's okay. This is okay. Then the question is, what is it not okay? For example, this is not okay. Here, what do you see? You see one point up there which is isolated from the other observations. So there is one very wide residual. And this is not okay. What happened to that observation? That would be called an outlier. So something which is lying out from the group. Why is it lying out? That's a question. Was there any error on that point? You see that R is helping us because if we go back to the graph here, we see that some points are highlighted. For example, the point number 1, it is highlighted because it has a very high value of residual. So R helps us. Of course, that is not an outlier because it's not particularly isolated. There are other residuals like that, almost like that. For example, this one, here. So we are more or less in line. But R says, look at the point number 1, and look at the point number 2, and look at the point number 9, because they are characterized by very high or very low residuals, high in absolute value. But this is not concerning me. This is concerning me because it's very isolated. So that is an outlier. And an outlier needs to be checked. Because if there was some mistake, particular error in that observation, perhaps it is worth removing that observation. because that increases the mean of the group to which it belongs. And such an increase, you remember that the mean is sensible to outliers. And if there was an error, we run the risk that such an error increases the mean, so we reach wrong conclusions. Of course, we are not allowed to remove data if we are not sure that there was a particular error in that data, because that might just mean that this phenomenon is characterized by high variability. So, very strange value can happen. And we can't remove a very strange value that can happen because we decrease the variability. And if we decrease the variability, the error variability, when we make our F-test, we have at the denominator a quantity which is lower than it should be. And if the denominator is lower than it should be, the F ratio is higher than it should be. So we reject the null, but in fact, we were not allowed to reject the null. So we need to be careful. If that is an error, but we need to be sure that that is an error, we remove it. If we are not sure that that is an error, then we should leave it inside, because it will tell us that there is high variability in the phenomenon. So we need to take careful decisions. So this is something wrong, at least not really wrong. It's something to care about. So first problem, outliers. And we spot them as isolated data. The outliers must be just a few. We cannot have 6, 7 outliers. That's impossible. It means that there is something wrong with the experiment. First. So if we have a lot of outliers, we should maybe throw the data set out, away. So remake the experiment. If we have a few outliers, then we check them. Was there any error? If we find an error, if we find an explanation for the outlier, then we are allowed to remove it. If we can't find an explanation, then we need to leave the outlier inside. We should never remove an outlier just to obtain a good fit. That's not an excuse. It's like removing whatever we cannot explain. And that's, if we can't explain something, that doesn't mean that it is not important or it is an error. It is just that we cannot explain it, but it's a part of the data, right? I have experience. I've been analyzing data for maybe 30 years now. And I've seen a lot of colleagues just removing data when they cannot explain them. And that's not correct. That's not to be done. It's not fair. Yeah, that's the first deviation. And this is a second deviation. You see, we see here a clear pattern. It's like a funnel. What does this mean? It means that when the expected values increases, the variability increases. So the variances are not homogeneous. Are not homogeneous because they increase when the average value increases. So treatments with low average have low variability, and treatments with high averages have high variability. So variances are not homogeneous. We need to be careful to this panel here. It can also be the other way around, less frequent. This is the most frequent one. And that's a clear sign that we have heteroscedasticity. So non-homogeneous variances. And that's a deviation from the basic assumptions. Then, yeah, that's another case, but less frequent with ANOVA models. That happens more with regression. But you see that we have negative residuals when the expected value is low, and positive residuals when the expected value is high. Here you see we have positive residuals, and here we have negative residuals. This is not normal because it's not a random positioning here. There is some pattern, and that's not normal because residuals should be random. If they are negative in one part and positive in another part, then the pattern is not random. There is a pattern. Yep. That's it. So this type of graph helps us with spotting outliers and heteroscedasticity. And it's very useful. But then we need another method to detect possible deviations from normality, so from the Gaussian assumption, which is important. Now we'll make another type of plot. I will, ciao Carlo, explain to you briefly. I'll take the residuals, epsilon. Here we go. I'm closing this window here for a while. The standard deviation of residuals, we know it is sigma. Oops. And here we go, 3.5 roughly. Right? So we have a standard deviation of 3.5. So if we divide the residual, so I'm writing epsilon s because that means standardized. Standardizing means subtracting the mean and dividing by the standard deviation. That is the standardization. We spoke about that at the beginning. In this case, the mean of residuals we know it is 0. So we do not have to subtract 0 because it means nothing. We simply divide by the standard deviation. So epsilons, it is equal to epsilon divided by the standard deviation of epsilon. So we obtain the standardized residuals. Look, the standard deviation of standardized residuals is, how much is it? Any idea? It is 1. Of course, the standard deviation is equal to the original standard deviation divided by the constant, in this case, the standard deviation, so it's 1. So the standardized residuals should be sampled from a Gaussian standardized Gaussian distribution. Clear? So we need to make sure that these residuals are sampled from a standardized Gaussian distribution. And now, how do we do this? We have a way to we have 16 residuals here. Look, 16. So we have a way to get, first of all, we sort them. So we put them in increasing order. So let me write epsilon SS standardized and sorted. So here are our residuals, standardized and sorted. I can try to get 16 residuals from a real standardized Gaussian distribution. And I can do this by using an R function. I will not tell you much, but the function is this one. P point 16, 1 to 16, and then Q, no. So I'm using two functions, one inside the other. P point, sorry, it is plural. Here we go. So look at this. These are 11, so I'm naming this function like here. That's to say that these are theoretical points from a standardized Gaussian distribution. So if I take 16 points from a standardized Gaussian distribution, these points should look like this. So, and you see that's interesting because they are like a normal distribution. They are symmetric. You see that this is the lowest one is minus 186, and the uppermost one is 186. So it's symmetric, the distribution. And that's the Gaussian distribution, which is symmetric. And if you take the median, you see that the median of this theoretical, there we go, it's 0. And that's good because the median of a standardized Gaussian is 0. And also if you calculate the mean of these theoretical points, that is 0. And that's good because we know that the standardized Gaussian has a mean equal to 0 and the standard deviation must be 1. Yeah, almost. There are some rounding errors, but that's typical standardized Gaussian distribution. So we can plot our residuals and these theoretical residuals one against the other and compare. So we can do plot our residuals standardized and sorted against the theoretical residuals. And here we go. And we obtain this graph here. So if the theoretical residuals are equal to our residuals, they should lie along the diagonal. Something like this. P equal 1. Oh gosh, that's a mistake. Okay. equal 0, B equal 1. Okay, that's better. Maybe we should do something like this. All right, so here we go. So that's easy to spot whether the residuals are Gaussian or not. Because we have on one side the theoretical residuals. They are certainly Gaussian because we draw them as Gaussian. And on the other side, we have our residuals. If the two series of data match, the graph, the points, should lie along the diagonal. And I drew the diagonal so that we can see whether our points are on the diagonal. Here we see some deviations, but they are slight deviations. Again, we cannot have precisely Gaussian points. Our points are precisely Gaussian because we drew them like that. But when we sample, we have a sampling error. But that's not more than sampling error. And here, now, Florinda, your problem is that your graphical output is too small. Look, if I make a very small graphical output and I try to plot, I get an error. Figure margins too large. You see here. So I need to increase the size of the graphical output. And then if I increase the size, then I get everything right. Please try this solution, whether it works. Otherwise, let me know. In the meantime, take the, yeah, that's okay, good. You don't have to feel sorry, Florinda. Ask all your questions. I'm very happy that you ask questions. You have any questions? And you can?
My question is, now our points are distributed diagonally. And we say that the points we create are Gaussian. So is it all right?
It is all right because the points, our residuals, look very similar to points which were created from a Gaussian. So it's something like taking something which is certainly correct and compare to something which we do not know whether it is correct. If the two series match, then our series is correct because it matches a correct one. It's like this. Now I have to show you how this is called QQ plot. QQ plot. QQ plot stands for quantile plot because we are comparing the quantiles from a standardized Gaussian with the quantiles of our residuals. Here we have a shortcut that is plot. We pass the model object and say which equal 2. Before it was which equal 1. Now plot mod which equal 2 and we get the same graph. And that's quick. So when let's make a first stop. Graphical analysis can be simply performed by using the plot method passing the model object. We write which equal 1 and which equal 2. The first graph helps us spot possible outliers and variance homogeneity, or perhaps better, heterogeneity. The second graph is a QQ plot, and we can see whether the residuals are Gaussian or not. That's all. Two simple comments. And you do not need to be able to make these graphs by hand, as we did. I did that just to show you where these graphs come from. And if you are curious, just go and take a look. But you need to be able to make these graphs by using these simple comments here. So you fit the model, and then you inspect the residuals. That's what you have to do. You need to inspect residuals. So it is it is terribly wrong not to inspect residuals. So I want to show you. Okay, Valeria, there was a question. Sorry, I do not see your questions immediately, because there are too many things I have to keep under control. And my glasses are... now, this point, I did not really give you a thorough explanation about this point, and I'd rather not give it to you. What we do is this. We have two functions, one inside the other. So let me show you. If I use the p-points function and ask for, let's say, 5 points. So 1, 2, 5. What does it tell me? It tells me what are the percentiles corresponding to these 5 observations. For example, if I have 5 observations, the third one is the median. And we know that because the median is the central observation. And we see that the function p-point says this is the median. The second observation is the 31st percentile. And the first observation is the 11.9th percentile. So this function is calculating the percentiles corresponding to our observations. If we put these percentiles within the Q-norm function, the Q-norm function calculates the percentiles. So, for example, minus 1.18 is the 11.9 percentile in a standardized Gaussian. The median is 0, and we knew that. So these are the corresponding percentiles. If I have 5 residuals, the residuals represent the percentiles for my population, for my sample. Then I compare with the corresponding percentiles in a standardized Gaussian. So what you're asking me, Valeria, is exactly this. That function you are asking me is useful to calculate the corresponding percentile, corresponding to our residuals, the corresponding percentiles in a standardized Gaussian. So I have 2 series of data, my residuals and the corresponding percentiles in a Gaussian distribution. And I can compare them. If my residuals are really Gaussian, they should match these theoretical percentiles. I hope this is clearer now. Valerio. Good. Thank you for your question. Other questions? If you don't have questions, I want to show you some situations with problems. Yeah, let's go to the presentation. This is a cuckoo plot. So I have just put a Gaussian distribution, a standardized Gaussian distribution here, and the resulting QQ plot, QQ plot. And you see, it's not, this was drawn by taking random residuals from a Gaussian distribution. You see there are some deviations. Of course, they are in the logic of sampling. So we are sampling, so we have some sampling error. But you see that the residuals stay along the diagonal. So a different distribution, different from a Gaussian, I mean, might be either asymmetric. So we have a distribution which is leaning, like the Pisa Tower on the right or on the left. Or we could have a distribution that is flatter than the Gaussian or more pointed. Okay, so we might have these deviations here. Here in this case, look at the Gaussian is red here. And this is another distribution which is not symmetric. You see that it is leaning to the left. You see that it's leaning to the left, and that means that we have a right skewed residuals. So if the residuals are right skewed, for example, log normal, they are not Gaussian. And we see that the QQ plot is like this. And it doesn't stay along the diagonal. It doesn't stay along the diagonal because here you see that this is the mean. The mean is perhaps here. So the median is lower than the mean because the distribution is asymmetric. And we have a lot of positive residuals, very high. And the negative residuals are less than in a Gaussian. So we have a low number of negative residuals and a high number of positive residuals. And that's why you see that we are staying up above the diagonal. And of course, if the distribution is, look at this, the red one is still symmetric, and the black one is asymmetric, but it's leaning to the right. And in this case, we have left skewed residuals. And if we have left skewed residuals, the QQ plot looks like this. Everything is below the diagonal. So these are possible deviations. And this is also interesting. Look at the red one. The red one is still Gaussian, and the black one is flatter, meaning we have more density on the tails and less density in the central part. That means we have a lot of outliers in this population. And you see the QQ plot looks like this. So you see the tails are deviating because we have more negative residuals than they should be and more positive residuals than they should be. Yeah. And this is another type of deviation. That's the last one. In this case, this is a uniform distribution, which is looks strange, but it's a distribution. This is the Gaussian, and you see that we have a higher level of density in the central part, and we have no outliers. In this case, here is the situation. Just take a look and take some practice. So this is good. This is not good. This is not good. So I think it's rather easy to spot. That? And here we go. And here again, the contrary. So look at the tail. if they deviate significantly, I can't say significantly because I don't have a test, but if they appear to deviate very much from the diagonal, then there is a problem, right? That's good. That's good. And what we have to do with it is just here we go, and here we go. And we don't see problems. I don't see problems here. They are right along the diagonal. No problems at all. So with our data set, it is okay. I'd like to show you another data set. Now, I'm copying this part here. So instead of mixture.csv, we load insects.csv. Sorry, do not pay attention to all these messages. It's complaining about my graphical window, which is too small. I'm cleaning the console. I'm cleaning the console, cleaning everything. And look at this data set. And I'd like to ask you, and okay, when you please tell me when you have finished loading this file, and then I will explain to you what it is about. So some okay are arriving. Good. So look at the insects.csv, everything small letters. Is that okay? You can? I'll tell you what this data set is about. We sprayed 15 leaves of tobacco with 3 insecticides. So 5 leaves per insecticide. So it's a completely randomized experiment. Insecticides are expected to control insects. After the treatment, we counted the number of insect eggs. So we counted the eggs. Now we need to be careful because with counts, we are far away from a Gaussian distribution because counts are discrete and the Gaussian distribution is made for continuous data. And counts are also, they have a plateau. They cannot be lower than 0. They cannot be negative. So the Gaussian might be negative. So when we have counts, we need to be very suspicious about having Gaussian residuals. So this is important. This is experience. When we have continuous data, then we can easily assume that the residuals are Gaussian. But with counts and proportions, we can't. So it's like with continuous data, there is a sort of assumption of innocence. So with continuous data, the residuals should be innocent. And they have to prove that they are guilty. But with counts and proportions, there is an assumption of guiltiness. So the residuals are guilty. And then we have to prove they are innocent. It's like reversing the problem. So here we need to be careful because probably counts are not Gaussian. And then we need to prove they are Gaussian. So, Kang, any problem? Is that okay? Right. So, now I'm enlarging here. We fit the model as we did before. So, mod. In this case, we use the function lm. We take the count and express the count as a function of the insecticide. Then we need to enter the data statement. So you see I'm using always the same names. I don't know whether this is right or wrong. It makes the code more easily reusable. Because if I change the data, I can just recycle the code, changing only a few things. For example, the name of the file. Then all the rest is similar. Of course, if you are inside a certain session, using always the same names might not be okay because I can cancel, erase object which might be useful. But for this simple analysis, using the same names is okay, really helps. So that's the model. Then we inspect the residuals. Simple, we do plot mod which equal 1. And then we get the first graph, the residuals against the expected. And here we go, and look, we see the funnel here. Here we have low data, low means, low counts with low variability, high counts with high variability, and high counts, high variability. And that's a sign of heteroscedasticity. Something's wrong. And I have an assumption of guiltiness. So I'm not able, it confirms my previous idea that counts are not normal and they are not homoscedastic. And if I ask for a cuckoo plot, so I simply replace which equal 1 with which equal 2. I draw the cuckoo plot, and you see, I have these two residuals here, and this one here, they are very far away from the diagonal. We don't see it because the diagonal is something like here. So you see that it's very similar to this situation here. Very similar. Look, I have just a little data. That's 15 data, which is really a few. Here are more, and I see them. I see the pattern more clearly, but it's very similar. In this condition, in the other conditions, with the other data set, I couldn't see any problem. So if I have continuous data, so there is a presumption of innocence, and I looked at the graphs and they didn't suggest any deviation, so I'm okay. But with this data, I have counts and they are guilty, and the first graph suggests strong deviation from homoscedasticity, and the second graph suggests strong deviations from normality. In this case, I can also insist and use a statistical test. We have two statistical tests. I will just mention them to you. If you look at the book, you will find some more explanation, but here I will just mention them. The first test is the Levine test, and it is, sorry, here we go. We can use, yeah, we do that by hand, or not? No, we do that by using the function. So I have a function which is inside a package. That's a common situation now. Not all the functions are implemented in the base R installation. So if we need additional functionalities, we need to install additional packages. Installing packages is very simple. We can do this by using the menu here, tools, install packages, and then I install the package car, right? So car, and then install. Of course, I have it already installed, so I don't need to install it again. But I installed in any case. But you have to do this. The other possibility is simply to use the console to install packages, and car. Here we go. That's exactly the same. I can use the menu, or either the menu or the console. Then, we have to load the library. So, before we install, but we need to install just once. Then we don't need to install once it is installed. What we need to do is to load the library by using the code library. And here we go. This is the code. And please confirm that you managed to install the package and to load it. Was okay? Was it okay? Yeah, I think so. Now you need to load the library card. So you load it in memory. And next time, you don't need to install. You just need to load. And you? That's okay? So remember that next time you don't need to install. Yeah, Florinda, you can do both. Yeah, well, not both. One of the two. You can use the menu or install by using the console. The result is always the same. And please remember that next time you don't need to install. You just need to load the library. So now we have the library installed and loaded. We can use the functions which are inside the library. And one of the functions is this one here, Levine test, right? So I'm writing Levine test. This is a test to test for homogeneity of variances. So the null hypothesis is that variances are homogeneous. So we need to see whether we can reject the null. If we reject the null, then we have a problem. If we can accept the null, then we have no problem. Here, I would expect that the null is rejected, because we already saw that we had counts and we had graphs with variance inhomogeneity. Right? So the syntax is rather similar to the syntax for fitting the model. Insecticide, the data. Now we can make the Levine test with respect to the mean or with respect to the median. We select the mean. Perhaps it is not the most correct decision, but it doesn't matter much in this stage. And here we go. So R gives us some output. That's the Levine's test for a homogeneity of variance. I use the mean instead of the median, but it doesn't matter at this stage. And we see that we have the group with 2 degrees of freedom because we have 3 insecticides. And if the null hypothesis is that there is homogeneity of variance, then we can reject the null because the p-value is below 0.05. So here we have a problem. That's a yes or no decision. Do we have a problem with variance homogeneity? The answer is yes. We have a problem. Houston, we have a problem. So, did you follow me to here? Is that okay? You? Is stuck somewhere? Sorry, no, I should. Yeah. I should not touch it. Seems to be stuck. It's stuck. You don't see the prompt. And it has been so we should see, right? It's not. Non benzina, no? Perché alla fine dovrai risultare. Sei girato sul Mac fa le bombe. Succede purtroppo. Okay. Yeah, you can. Sarah is. Yeah, now she can see it. Okay, so she made an answer and she gave her the response already. Yeah, it's significant. Unfortunately, Claudia got stuck. The R session froze. Well, this is not fundamental to me, making these tests. I very seldom do them because I tend to look at graphs and decide. With continuous data, I'm usually rather flexible. I accept a small degree of problems. With counts and proportion, I tend to not to consider them Gaussian and with homogeneous variances. I tend to be very strict. That's my approach. But please do not make up your mind too much with these assumptions. Try to, first of all, check them, and then, in case of problems, you take some measure. And I will show you what measures you have to take. So, it must be, you must use a lot of common sense by approaching these diagnostic tools. Because you very often obtain contradictory results. You sometimes have graphs where you do not know whether the residuals are Gaussian or not, the variances are homogeneous or not. And also these tests tend not to be very powerful. So sometimes you reject the null. If you have a lot of data, you reject the null, but you are never sure that the variances are homogeneous. I want to show you another thing, which is the Shapiro test. And we pass the residuals. So residual mode. And this is to establish whether the residuals are Gaussian or not. And it's, yeah, we see here, again, a p-value, it's 0.04. So here again, we reject the null, and the residuals are not Gaussian. So another sign that something is wrong here. So here we are pretty sure. We have counts. The two graphs gave us suspects. And the Levine's test is significant, and the Shapiro test is significant. Everything says that we have a problem here. I have the idea that we should stop it here, because now we have to study the solutions. But I think I said a lot of things today. So what did I say? I said, first of all, whenever we fit a model, immediately after fitting the model, first thing to do is to check the residuals. That's your roadmap. First, fit the model. Second, check the residuals. And then take a decision. If the residuals are okay, you go ahead. And that is our first data set here. If the residuals are not okay, then we need to take some measure to correct, we say, stabilize the data. So we need to adopt some stabilization measure. It's like discovering that we have some illness, then we have to take a medicine. It's like here. If we discover that the data have some illness, then we need to take a medicine. What is the medicine? We will see tomorrow, if you agree. I will put this code and the slides online in Unistudium, plus the book chapter about these aspects here, because it's already almost okay. I want to tell you that all the book chapters are in English, but there is the corresponding Italian translation, and you notice them. So for the Italians, you might want to look at the Italian translation. Please remember that it's not a real translation, because now I'm translating the book, and while translating it, I'm making changes. So you will see a lot of differences, which I have still to correct on the Italian version. It's difficult to keep two versions at the same time.